Hi and welcome to the videos for section 3.4. This is the first of two videos. In this section, we're going to be looking at what's known as real zeros of polynomials. So in this first video, let's look at the polynomial. So p of x is equal to x minus 2 times x minus 3 times x plus 4. If you were to multiply this whole thing out, you're going to get x to the third minus x squared minus 14x plus 24. So, let's look at this polynomial. This guy here, 1, comes from what? Our 1 times 1 times 1. The coefficients of the different factors that we had. And what about this 24? Well, this is what? This is negative 2 times negative 3 times positive 4. The values that we actually see inside of our factors. So these values, the negative 2, the negative 3, the positive 4, this tells us that the zeros of a polynomial the zeros of a polynomial are all factors of the constant term. So all of these zeros were factors of the 24, plus or minus 2, plus or minus 3, plus or minus 4, a combination of those. This gives us what's known as the rational zero theorem, or you might also hear it sometimes called the rational root theorem. Now, rational, remember back to, I think, our very first video, we talked about rational numbers. And when we had talked about the word rational, we knew what? We're looking at ratio. And that says the following. If the polynomial p of x, which is equal to a to the n, x to the n power, plus a to the n minus 1, x to the n minus 1, plus, etc., a to the first, x to the first power, plus a to the 0 are constant. So if we have that general form of a polynomial, this polynomial has if this polynomial has integer coefficients, then every rational zero of p is of the form p over q, where p is a factor of a0, a0, our constant term. So that goes in the numerator. And q is a factor of a to the an. So the coefficient of our highest degree term, one of the factors of that goes in the denominator. our constant, one of its factors goes in the numerator. This ratio is going to be a 0 or a root of this polynomial. So let's look at an example. So we want to find, let me see here. One more thing before we do the example. So we also have our sign change rule. And what this says, this is before we even try to figure out how many zeros we have of a polynomial, how many positive and how many negative, we can use the sign change rule. So when we take our p of x, this has a positive number of zeros or less by 2's. And so when we look at the example, I'll explain sort of what this means, but we're going to take our polynomial, we'll look at it, and however many times the sign changes from positive to negative, or vice versa. As many times as it changes, that's how many positive zeros we have, or less by 2. So if we have, let's say, 3 sign changes, it's either 3 or 1, go down by a value of 2. If it was 6 sign changes, it would be 6 or 4 or 2 or 0. Keep deducting 2's. The negative number of zeros, or less by 2, that occurs when we do p of negative x. So we plug a minus x into the polynomial, clean it up, simplify it. That tells us how many, depending on the sign changes, how many negative zeros we have. And really, as long as we're plugging in negative x, any of the even terms will just stay as they are. Any of the odd terms, so x to the 5th, x to the 3rd, x to the 1st, those are all going to get sign changes. So we can kind of just go in shortcut and change all those signs up. So now let's look at an example using both of these, our rational root theorem, as well as our sign change rule, to get an idea of how many of positive or negative roots we have. So, an example, find the rational zeros of p of x is equal to x to the 3rd minus 3x plus 2. So, first thing, possible positive roots. This comes from our sign change rule. I start at positive, switches to negative, that's 1 sign change. Switches to positive, that's 2 sign changes. So my possible number of roots is either 2 or 0. Drop it down by a degree of 2. For the negatives, so let me switch to blue so we can keep it straight here. I need to figure out p of minus x. And as I told you, if it's an x squared and then x squared and negative x, it's just going to change it back to positive. So all I have to do is anywhere I have an odd degree term, change it. So this is positive, it's going to become negative. This is x to the 1st, so its sign is going to change. And then plus 2, well that's like 2x to the 0 power, so that doesn't get a sign change. It's only the values of x that have an odd degree exponent, 1, 3, 5, 7, 9, etc. So the possible number of negative roots is what? I start at negative, I go to positive, that's 1. I stay at positive, so I have 1 negative root in either 2 or 0 possible roots. Well, what's the degree of my polynomials? Degree of 3. So I'm going to have how many roots? 3 roots, which means I have what? 1 negative and 2 positive. So now I know how many possible positive, how many possible negative, so let's figure out what are the possible roots. So this is using my rational root theorem. And it's what? It's P over Q, where my values of P come from here. Well, what's my factors of 2? This is 1 times 2. So my only possible factors are 1 and 2. And here, my coefficient of the highest degree term is 1. Well, what's my factors of 1? It's just 1 and 1. So the possible roots are what? It's plus or minus, because 2 could also be what? It could be negative 1 times negative 2 also gives me a positive 2. So my possible roots are, and this as well could be negative 1 times negative 1. So I got to account for all the pluses and minuses here. So I get what? I get plus 1 over plus 1, plus 1 over negative 1, and then plus 2 over plus 1, and negative 2 over negative 1. And I also have the negatives here. So negative 1 over plus 1, negative 1 over negative 1. Oh, this should have been a plus 2. So plus 2 over plus 1, plus 2 over minus 1. Now the negatives, negative 2 over positive 1, negative 2 over negative 1. So there's 8 possibilities here, really. But let's look at, is there really 8? This is what? 1 over 1 is positive 1. That's the same as negative 1 divided by negative 1. So these pluses and minuses sort of start canceling each other out. This is negative 1, same as this one. And then that's it, I think. So this is plus 2, up now. So this is plus 2, same as this end one. And this is negative 2, same as negative 2 over positive 1. So there's really only, where did my negative go here? Oh yeah, this is negative 1. So this is what? The possible roots are 1, negative 1, positive 2, and negative 2. And anytime we have 1 as our coefficient, that's how it's going to work out. Just the positive and negatives of the last term, whatever its factors are. So that's our possible roots. Now, how do we figure out what's actually a root? Well, that's our synthetic division, or it's our remainder theorem, right? So if I know what the possible values are, then I can find the zeros simply by plugging them in. Because if I plug in these values, if they're a root, my remainder is going to be 0. So by the remainder theorem, I'm looking for when P1 equals 0, P of negative 1 equals 0, P of 2 equals 0, or P of negative 2 equals 0. So if I plug those in, I get 1 to the third minus 3 times 1 plus 2. So that's what? That's 1 minus 3 plus 2 is 0. Okay, good. So that means that 1 is one of my roots. Positive 1. How about if I plug in negative 1? Negative 1 to the third minus 3 times negative 1 plus 2. So that's negative 1 plus 3 plus 2. That's not equal to 0. That's equal to 4. So that equals 4, which is not 0. So negative 1 is not a possible root. How about 2? If I plug in 2, I get 2 to the third minus 3 times 2 plus 2, that's 8, minus 6 plus 2, that's 10 minus 6, that's also 4. So positive 2 is not a root. And I know what? I know I have one possible positive root, which means at this point that's the only thing left, so I know negative 2 has to be a root here. Because by the change of sign rule, I have to have a positive root. A possible negative root. That's all that's left is the negative 2, but let's double check. we get negative 2 to the third minus 3 times negative 2 plus 2. That's negative 8 plus 6 plus 2. 8 minus 8 is 0. So that's good. So our roots are what? Negative 2 and 1, but we knew we needed 3 possible roots because we had a degree 3 polynomial, and we know we needed 2 possible roots, or 2 positive or 0 positive. So really our roots are what? It's 1 and negative 2. If we had to put it into a bunch of parentheses and multiply it out, if it said what are the factors, then it would be what? X minus 1, x minus 1, x plus 2, because we have to account for that negative sign change. So for this one, if we just have to find the rational zeros, we need to figure out what's our possible roots, use our remainder theorem, crunch the numbers, and wherever we get a 0, that gives us our values. So come on back, we'll look at a little more complex examples, and that'll wrap up the videos for section 3-4.